So this is carrying on with our gas laws review, and the first question under our chart on the review sheet says, how many grams of lithium gas must be in a 15.6 liter container to exert a pressure of 0.78 atmospheres at a temperature of 25 degrees Celsius? So the first thing we want to do anytime that we're doing any kind of word problems in science or in math is we want to identify the variables that were given. So it said how many grams of lithium gas. So we have a lithium and we have a 15.6 liter. So that's going to be our volume. And it wants to know that it exerts a pressure of 0.78 atmospheres. And it has a temperature of 25 degrees C. So that's our temperature, and it wants to know how many grams of lithium. So we look at what we're given. We're given volume, we're given pressure, we're given temperature, and it wants to know grams, so we know that we're probably solving for moles that we can convert to grams. So we want to use our friend PivNerd. So we select our equation and we write our equation down. Then we check our units that we have. We have pressure in atmospheres, we have volume in liters, we have temperature in Celsius. And we know that when we're dealing with gas laws, we always want our temperature in Kelvin. So we're going to add 273 to that to get a temperature of 298 Kelvin. And we're going to substitute that into our problem, and we get 70.78 atmospheres times 15.6 liters. I'm keeping my units as I work through my problems because I know that that will help keep me straight and it will help get me a better grade on the test. I'm solving for moles, so if I rearrange my equation, I will put my R 0.0821 liter atmospheres per mole Kelvin, and our temperature of 298 Kelvin. And we can see that our liters will cancel, our atmospheres will cancel, our Kelvin will cancel, and we're left with moles. And when we do all the math there, we find that that is 0.5 moles of lithium. But the question asked for how many grams of lithium gas we had, so we want to convert that to grams by our conversion table. In 1 mole, we look at our friend Mr. Periodic Table and we see that there's 6.9 grams of lithium in every mole, and so we multiply and we get 3.5 grams of lithium gas as our answer. So the next problem says that we want to calculate the mole fraction of potassium nitrate in a 9-mole aqueous solution. So you always have trouble saying that word, but we know that it's a small m, so we know that that's a molal concentration, and when we're dealing with molality, we know that it equals moles per kilogram of solvent. So we know that if we have a concentration of potassium nitrate, we want to also write down our formula for that. We have potassium nitrate. Yes, you're going to have to know your polyatomic ions until the end of chemistry. We know that this is 9 moles. We were given that molality equals 9m, so that means that there are 9 moles in every kilogram of solvent, and we aren't given a mass, so we can choose whatever mass of water we want. We want to make it easy on ourselves, so we're going to say that there's 1 kilogram of water, and so that we can say there's 9 moles in that 1 kilogram of water. So to figure out how many moles we have, we're using the 1, so it'll just turn out that there's 9 moles of potassium nitrate in there. And so we also need to know when we're dealing with mole fractions. So remember the mole fraction of anything. So the mole fraction of potassium nitrate is going to be equal to the number of moles of potassium nitrate divided by our total moles in our solution. So we know our total moles of potassium nitrate. We need to also figure out our total moles of water so that we can add those together to get the total moles in the solution. So we need to calculate the number of moles in a kilogram of water. So 1 kilogram of water is 1,000 grams of water. We know the mass of water is 18.02 grams per mole. And so we can convert that, and we know that we have 55.56 moles of water. So we add those together and substitute them into our mole fraction equation, and we know that we have 9 moles divided by 55.56 moles of water plus the 9 moles of potassium nitrate that are in that solution. And so we find that the mole fraction is equal to 0.139. Remember that our mole fraction doesn't have units because we're dividing moles by moles. And so we either can say that our mole fraction is 0.139, or we can say 13.9% of the solution of potassium nitrate is the potassium nitrate molecules. So remember that mole fractions is simply another way of looking at a ratio, the percentage of whatever molecule you're looking at in solution. Number 3 on our worksheet says that a sample of hydrogen exerts a pressure of 155 kilopascals at 37 degrees C. The gas is heated to 77 degrees C, but remains at a constant volume. So volume 1 equals volume 2. So what will be the new pressure? So we want to identify that this is our pressure 1, this is our temperature 1, this is our temperature 2. We know the volume doesn't change, so we don't need to use it in our equation. We could use the combined gas law, but since we only have pressure and temperature, we can go ahead and use Charles' law, which says pressure over temperature equals pressure over temperature. Our temperatures are in Celsius, so we need to add 273 to each one of those. You have to be really careful to convert to Kelvin because otherwise you will not get the right answer. We do not need to change our pressure. We can keep it in pascals unless it asks for something else, which of course it does. It asks for the pressure in atmospheres. So we'll do that at the end. So we'll substitute in. Our initial pressure is 155 kilopascals divided by 273 plus 37, which is 310, and that will equal our other pressure divided by 273 plus 77, which is 350. When we have our fractions, you have to be very careful with your algebra so that you do it correctly. In order to get this out of the bottom, you're going to multiply both sides by that, so you can put your 350 up here, multiply it by that, and that will give you your pressure. And that will equal 175 kilopascals, but as I pointed out, I want the answers in atmospheres, so we'll take 175 kilopascals, and we know that there are 101.325 kilopascals in an atmosphere. And so we do the math there, and we end up with 1.73 atmospheres. So I hope that you're taking the time to work through these problems and not just watching me solve them, and that you're figuring out how, if you identify your variables and pick out your equation, then you can substitute those in to solve. So number 4 says that we have an unknown gas with a density of 3.739 grams per liter at STP. So at STP we know that the temperature is 273 Kelvin. We know that the pressure is 1 atmosphere. So that makes us happy. They're nice and easy to work with. And we're given a list of gases that we can choose from when we get to the end. So on a worksheet that I gave out earlier, there was a whole derivation of using the density formula and substituting it into PivNert. And we ended up with an equation that says the molar mass, or the atomic mass, of a substance is equal to, times its pressure, will equal its density times R times temperature. So we can use this formula to determine the identity of a gas by finding out what its molar mass is. We solve for molar mass by dividing both sides by pressure. That moves that variable over. And once we know the molar mass, we can look at our atomic, or at our friend in the periodic table, and find out what the gas is. So we substitute in. Density is 3.739 grams per liter. R is our favorite, 0.0821 liter atmospheres per moles Kelvin. And our temperature is 273 Kelvin. And our pressure, yay, is 1 atmosphere. So that makes the math easy. And we end up with a density of 83.8 grams per mole. And we get that by our atmospheres cancel each other. Our liters, our kelvins cancel each other, and so we're left with grams per liter, and we know it's an ideal gas, so we know that there's 22.4 grams per every liter per mole, and so we can say that's grams per mole. And we look at our friend the periodic chart, and we see what has a molar mass of 83.8, and it turns out that the closest thing is krypton. So we can say that, given these situations, the gas we're dealing with is krypton.